All right, let's dive right in. Today, we're talking about two of the biggest ideas in, well, the entire universe, time and motion. It's a huge topic, but the story of how we learn to measure them, from watching the seasons to counting nanoseconds, is really the story of human creativity. It's going to be a fun one.
So our whole journey today really kicks off with this one simple question. Imagine you're watching a race, right? And you see these sprinters just fly by. It makes you wonder, before we had stopwatches, before we had any clocks at all, how on earth did people measure something that happens in the blink of an eye? That question is exactly where we're going to start.
So, Section 1, a question of time. Let's wind the clock all the way back, way back. Before any kind of technology, our ancestors were looking up at the sky and all around them, because nature had its own clocks.
And, they were incredible observers. They saw that the universe has this steady, reliable rhythm. The sun comes up, the sun goes down. That's a day. The moon goes through its phases. That's a month. The seasons change and come back again. That's a year. These huge, natural cycles were humanity's very first clocks, our very first calendars.
Okay, but what about smaller bits of time? Like, how do you measure just a few hours within a single day? For that, people had to get really creative. They had to invent their own time machines. And for centuries, we basically relied on these four brilliant inventions. You had sundials, of course, tracking the sun's shadow. You had water clocks, which used the steady drip of water. Hourglasses with their falling sand, which we still see today. And even candle clocks. Candles marked with lines that would tell you how much time had passed as they burned down. So clever.
Now, don't think for a second that these ancient tools were basic. Some of them were incredibly precise. Take the Samrat Yantra in India. This thing isn't just a sundial, it's a massive, beautiful stone instrument. And it's so accurate, it can measure time down to 2-second chunks. That's just amazing for something that's 300 years old and runs on nothing but sunlight.
And what's really cool is that this ancient tech is surprisingly simple. The idea behind a water clock is so straightforward, you could actually build one right now with just a plastic bottle. It's a great way to kind of connect with that ancient ingenuity, you know?
All right, now we get to a huge turning point in our story, a massive breakthrough. And it didn't happen in some fancy laboratory, it happened in a church. And it would completely change how we keep time, forever.
So the story goes like this. Galileo Galilei is just sitting in a cathedral, probably a little bored, and he starts watching this lamp swinging from the ceiling. He didn't have a watch, of course, so he used the only timer he had on him, his own pulse. And as he's timing the swings, he discovers something incredible. It didn't matter if the lamp was making a big, wide swing or a tiny little one, each swing took the exact same amount of time.
And that single observation led to this fundamental concept in physics, the time period. It's just a fancy term for the amount of time it takes a pendulum to complete one full swing, all the way to one side, all the way to the other, and back again, one oscillation.
So here's the kicker, the really crucial part that Galileo figured out. The time it takes for a pendulum to swing depends on one thing and one thing only, how long the string is. It doesn't depend on how heavy the weight is at the end. That consistent, predictable motion became the beating heart of the first really accurate mechanical clocks, which were invented by Christian Huygens. It was a total game changer.
So Galileo's pendulum basically kicks off this huge technological race for more and more precision. It's a race that's still going on today, and it's why the timekeeping devices we have are so unbelievably accurate.
I mean, just look at this journey. We start with those pendulum clocks, which were absolutely revolutionary, but they'd still lose, maybe 10 seconds a day. Then in the 20th century, we get quartz clocks. They use the super fast vibrations of a tiny crystal to keep time, and they were a massive leap forward in accuracy. And that, of course, brings us to today and the atomic clock.
And this, right here, just shows how absolutely insane our progress has been. Today's atomic clocks are so precise, it's almost impossible to wrap your head around. They would lose only a single second over millions of years. It's that level of accuracy that makes things like your phone's GPS or high-speed internet even possible.
Okay, so we've totally mastered measuring time. Now let's connect that to another big idea, motion. This brings us to a word we all use every day, speed. And the relationship here is really simple. If you know how far something went and you know how long it took to get there, you can figure out its speed. It's just the total distance you covered divided by the total time it took. Simple as that.
Let's look at a quick example to make this super clear. We've got two trains here, train X and train Y. Now look closely at train X. See how in every single 10-minute period it travels exactly 20 kilometers? It's perfectly consistent. But now look at train Y. Its distances are all over the place. And that little difference is the key to understanding the two basic types of motion.
So this table shows it perfectly. Train X is in what we call uniform motion. It's moving at a constant speed. Think of it like a car with cruise control set on a long, empty highway. Train Y, on the other hand, is in non-uniform motion. Its speed is always changing. That's like a car in city traffic. You're speeding up, you're slowing down, you're stopping. That's real life for most of us, right?
So after this whole journey from sundials to atoms, here's the really wild thought to leave you with. We have become absolute masters at measuring the passage of time. We can chop it up into unbelievably tiny slices with incredible precision. But that basic question, what time actually is, well, that's still one of the biggest, deepest mysteries in all of science. Something to think about, huh?